This is Unknown Genesis 4K, the planet in its most raw, most powerful, and most unfiltered form. If this is your first time here, hit subscribe, because what you're about to see is only the beginning. Antarctica is imagined almost universally as a place of absolute stillness, a continent suspended in white silence, sealed beneath ice so ancient that its compression holds air from a world that no longer exists. When people picture it, they picture something frozen outside time, a place where change itself has been paused, where the ordinary laws of motion and growth and decay have been placed indefinitely on hold. That image is not wrong, but it is radically incomplete. Because Antarctica has an edge, and at that edge, everything changes. The interior of the continent may hold its quiet. The vast white plateau at the center, where the ice sheet rises to more than 3,000 meters above sea level, and the air is so dry it can crack the skin, and the silence is so complete it has a texture of its own. That interior earns its reputation for stillness, but the edge is something else entirely. The edge is where the frozen world collides with the moving one, where ice meets ocean, where cold meets current, where the continent that built itself over millions of years in geological solitude finally encounters the restless, heaving, indifferent energy of the Southern Ocean. At the edge, Antarctica is alive in ways that the interior never is. It moves, it breaks, it carves, it shifts and groans, and releases pieces of itself into the sea. It breathes in the manner of living things, drawing in the cold and releasing it, contracting in winter and stretching outward when the light returns. The living border of Antarctica is not a line. It is a zone, a contested and dynamic threshold where land and sea and ice and sky negotiate their boundaries every single day, and where the negotiation is never, ever settled. This is the story of that edge, of what it looks like, what it does, what lives along it, and what it means for the planet that contains it. This is the story of one of the most dangerous, most beautiful, and most consequential places on the surface of the Earth. A place that most humans will never see with their own eyes, and that all of us are connected to in ways that go far deeper than geography. The living border, where nothing stays in one place. To understand the Antarctic edge, you must first abandon the concept of a fixed coastline. In most of the world, a coastline is a line, a boundary between land and sea that may shift slightly with the tides, that erodes gradually over human timescales, but that is, for practical purposes, a defined and knowable edge. You can mark it on a chart, you can sail along it. You can build a lighthouse on it and trust that the lighthouse will remain where you placed it for a generation or more. The Antarctic edge is nothing like this. It is not a line. It is a system, a complex, dynamic, seasonally variable system in which the categories of land and sea and ice are constantly renegotiating their boundaries. What looks like solid ground from the air may be an ice shelf floating on dark water. What looks like open sea in summer may be sealed beneath meters of fast ice by the following winter. What appears to be a fixed and navigable bay may have been reshaped entirely by a calving event that happened while no one was watching. The continent itself, the actual rock, the land beneath all that ice, is real and fixed. It has not moved in any meaningful human sense. But the ice that covers it, and the shelf ice that extends beyond it over the ocean, and the sea ice that forms and melts around it every year, all of this is in motion. Constant, complex, sometimes imperceptible, and sometimes sudden motion that makes the edge of Antarctica one of the most difficult environments in the world to navigate and one of the most fascinating to understand. Sea ice is the most obvious expression of this dynamism. Every Antarctic winter, the ocean around the continent freezes outward from the edge, extending the effective boundary of the frozen world by hundreds of kilometers in every direction. At its maximum winter extent, the sea ice surrounding Antarctica roughly doubles the size of the continent's footprint on the ocean's surface. Then, as the sun returns in spring and summer, this ice retreats, breaking apart, melting, drifting northward on currents, dissolving back into the ocean from which it formed. This annual expansion and contraction creates a coastline that must be redrawn on every seasonal chart. A route that was navigable in February may be completely sealed in July. A lead of open water that a ship threaded through one year may not exist at all the next. The Antarctic margin is a map that the planet rewrites every season in a script of ice and current and wind that demands constant attention from anyone who enters it. Icebergs introduce another layer of uncertainty into this already complex picture. They break from the edges of glaciers and ice shelves, sometimes in small fragments, sometimes in pieces that dwarf entire cities, and then drift northward on the Antarctic circumpolar current, carried by wind and water at speeds and along routes that are broadly predictable but never precisely so. An iceberg in fog is one of the most dangerous objects in the Southern Ocean. Its visible portion above the water is often the smallest part of its total mass, and its underwater body may extend outward in directions that have nothing to do with the shape of the ice that is visible from the surface. Cold bays along the Antarctic coast concentrate all of these elements simultaneously. A ship moving through a bay in the Antarctic summer may encounter grounded bergs that have lodged on underwater features and risen above the surface like sculpted monuments. It may thread through fields of brash ice, the broken remnants of bergs and sea ice that grind against each other in the swell. It may pass alongside ice shelf edges where enormous walls of blue-white ice drop vertically into dark water, their base invisible, their extent unknown. And it may do all of this in conditions of rapidly changing visibility where fog can close in within minutes and reduce the navigable world to a circle of water barely larger than the ship itself. For wildlife, this perpetual instability is not a problem to be managed. It is the habitat itself. The animals that live and feed at the Antarctic edge, the penguins, the seals, the whales, the seabirds, have evolved over millions of years to exploit precisely this kind of dynamic, shifting environment. They follow the ice edge as it advances and retreats. They use the boundary between frozen and liquid water as a feeding ground because it is at that boundary that the richest concentrations of the small organisms that sustain Antarctic food webs are found. The uncertainty that makes the edge dangerous for human visitors is the foundation of the biological wealth that makes it one of the most productive marine ecosystems on Earth. For humans, the same environment demands a particular kind of humility. The tools that have given modern civilization such confidence in its ability to navigate and manage the natural world. The satellite imagery, the ice-strengthened hulls, the weather forecasting models are useful here and sometimes essential. But they do not eliminate the fundamental challenge of operating in a place where the ground is not fixed, where the charts are provisional, where the weather can deteriorate from manageable to dangerous in the time it takes to make a decision, and where the consequences of errors are amplified by remoteness, cold, and the absence of any nearby assistance. The Antarctic Edge teaches, above everything else, that the natural world is under no obligation to behave like a fixed and predictable backdrop to human activity. Here, the environment is the protagonist. Everything else, every ship, every research station, every instrument array, exists at its sufferance. Nothing here stays in one category for long. Ice can float, sea can freeze, shelves can split, and water can open a path that was solid white only months before. The danger comes from that uncertainty. A route can close, a flow can shift, a crack can widen, and a calm-looking bay can suddenly reveal movement hidden beneath snow, fog, tide, and cold light. The Antarctic Edge is not a simple coastline. It is a restless border of land, shelf ice, dark water, and drifting bergs where the frozen continent is always changing shape as it meets the ocean, always in motion, always in negotiation, always alive. The Southern Ocean, the first and fiercest frontier. Before Antarctica reveals itself in ice, the traveler must cross the Southern Ocean. And the Southern Ocean does not welcome visitors passively. It tests them. It pushes back against every approach with a combination of wind, wave, current, cold, and ice that makes every successful transit feel like something earned rather than simply accomplished. The Southern Ocean is unique among the world's ocean basins in one fundamental way. It has no beginning and no end. It circles the planet at the latitudes south of approximately 60 degrees, encountering no significant landmass to interrupt its circulation. The other great oceans are contained by continental margins that constrain their circulation patterns and moderate their energy. The Southern Ocean has no such constraints. Its waters circle Antarctica in an unbroken ring, and the winds that drive them do the same. This uninterrupted fetch, the distance over which wind can act on water to build waves, is what gives the Southern Ocean its legendary character. Winds that blow consistently from the west across thousands of kilometers of open water build waves of extraordinary size and persistence. The swells that travel through the Southern Ocean are among the longest and most powerful on Earth. They arrive not as the chaotic, confused seas of a local storm, but as long, organized ridges of water that have traveled enormous distances, maintaining their energy and their structure across ocean basins. A ship in the Southern Ocean can encounter swells generated by a storm that occurred thousands of kilometers away, and days in the past, the energy still propagating forward with the patience of something that has all the time in the world. The swell can arrive from weather far beyond sight. A vessel may meet waves born days earlier, lifted by distant storms, carrying the memory of the Southern Ocean before land becomes visible ahead at all. The roaring 40s, the furious 50s, the screaming 60s. These are the old names that sailors gave to the latitudinal bands of the Southern Ocean, each one marking a zone of progressively more intense wind and sea. The names were earned through experience, through the accumulation of voyages in sailing ships that could do nothing to fight the weather and could only work with it, using it to drive them eastward around the bottom of the world. Those routes were quicker than fighting contrary winds elsewhere, but they demanded an absolute respect for the ocean's power, a respect that those who underestimated it paid for with their lives. Modern ships are enormously more capable than those old sailing vessels. They have engines powerful enough to make headway against conditions that would have stopped a sailing ship cold. They have stabilization systems, weather routing software, and ice-strengthened hulls that allow them to go where their predecessors could not. And yet, in the Southern Ocean, none of this fully insulates them from the basic reality of the environment. The swells still lift them. The wind still howls through their superstructure. The ice still appears from fog in ways that demand immediate responses. The most experienced polar mariners speak of the Southern Ocean with a respect that has no equivalent in any other water they have sailed. Cold currents add another layer of resistance. The Antarctic Circumpolar Current, the largest ocean current on Earth by volume, sweeps eastward around the continent, with a force that shapes the thermal structure of the entire Southern Ocean and, through that, the thermal structure of the global ocean system. It moves around Antarctica like a living belt, shaping temperature, feeding the sea, and reminding every traveler that this ocean is part of the continent's defense. The polar front, sometimes called the Antarctic Convergence, is the boundary where cold Antarctic surface water meets the warmer subantarctic water from the north. Crossing this boundary is a transition that every vessel approaching Antarctica experiences physically. The sudden drop in air and water temperature, the change in the color of the sea, the appearance of the first albatrosses and petrels that follow the cold water southward. It is an invisible line in the ocean, but it is a real and consequential one, marking the outer edge of the Antarctic system as clearly as any physical boundary could. Drifting ice complicates the final approach in ways that cannot be fully anticipated, regardless of how good the satellite imagery is. Ice conditions change faster than the satellite's overpass. A lead of open water visible in a morning image may be closed by afternoon wind and current. A field of scattered floes that looked navigable from the chart may, on the water, reveal itself as a tight and impenetrable pack. The polar navigator must maintain a constant dialogue between the information provided by remote sensing and the direct evidence of their own senses. The look of the ice from the bridge, the sound of it against the hull. The behavior of the ship as it encounters different ice types. This is why the Antarctic Edge begins before the ice shelf itself. It begins in rough water, low cloud, sharp wind, and the feeling that the ocean is testing every vessel, before allowing it any closer. The Southern Ocean does not behave like a simple passage. It surrounds Antarctica with motion, building a natural barrier of waves, storms, cold spray, and uncertainty that no map can soften completely. And yet, for all its hostility to human passage, the Southern Ocean is not hostile to life. Quite the opposite. The upwelling of cold, nutrient-rich water from the deep ocean, driven by the powerful currents and winds of the region, creates conditions of extraordinary biological productivity. The phytoplankton blooms that develop in the Southern Ocean in spring and summer are among the most extensive on Earth, covering vast areas of sea surface with a film of photosynthetic life that forms the base of one of the most important food webs on the planet. The same ocean that resists humans prepares the feast waiting at the Antarctic Edge. So the journey to Antarctica starts at sea, not on snow. The Southern Ocean is the first frontier, a fierce ring of wind, current, wave, and ice that makes the frozen continent feel protected by the planet itself. It guards what lies beyond with a patience and a power that no engineering has ever fully matched, and that no traveler who has crossed it ever entirely forgets. Icebergs, the floating architecture of a continent. After the Southern Ocean has been crossed, Antarctica announces itself through ice. Not through land, not through the gradual rising of a coastline on the horizon, but through the appearance of white shapes in the water, first distant and uncertain, then closer and undeniable. Icebergs. An iceberg, seen for the first time, has an effect on the human nervous system that is difficult to describe and impossible to forget. It has a quality that is unlike any other natural object encountered at sea. It does not look temporary. It looks architectural, like something built, like something placed deliberately in the water by a hand of unimaginable scale. Its faces are vertical and smooth. Its edges are precise. Its colors shift through a spectrum that ranges from the blinding white of its snow-covered upper surface through the pale blue of compressed ice to a deep, almost luminous turquoise, where light penetrates the clearest and most ancient ice at the waterline. But the appearance of permanence and solidity is a profound deception. An iceberg is one of the most dynamic and dangerous structures in the ocean, precisely because what you can see is only the smallest part of what is there. The portions of an iceberg visible above the waterline typically represent no more than 10 to 15% of its total mass. The remaining 85 to 90% lies below the surface, extending outward in ways that often bear no relationship to the shape of the visible ice above. The underwater body of a large iceberg may extend tens of meters or more beyond the base of the visible cliff, invisible, undetectable by eye, and capable of destroying any vessel that ventures too close without taking careful soundings. An iceberg is never only what the eye sees. Its bright towers rise above the sea while most of its mass hides below, heavy, blue, and unpredictably drifting through water like a fortress with a buried foundation. This hidden size changes the danger completely. A vessel may pass a shining cliff of ice, yet beneath the surface, a much wider body reaches outward, shaped by melt, pressure, balance, and cold, dark water. tabular icebergs, the flat-topped giants that calve from ice shelves, can be extraordinary in their dimensions. The largest icebergs ever recorded have exceeded the area of small countries, stretching for hundreds of kilometers and rising tens of meters above the waterline. These great white platforms drift through the Southern Ocean on their slow journeys northward, gradually melting and eroding, their edges calving smaller bergs and brash ice into the water around them, their underwater keels scraping across underwater ridges as they move. Their passage reshapes the seafloor. Their meltwater influences ocean circulation. Their presence changes local sea ice conditions across enormous areas. Smaller icebergs are more numerous and in some ways more immediately dangerous than the giants. The great tabular bergs are usually easy to see and avoid. The smaller, irregular bergs, the kind that result from the gradual weathering and erosion of larger pieces, or that calve from glaciers in mountainous coastal regions, can have shapes that make them difficult to detect in poor visibility, especially when spray, fog, or low light reduce the contrast between the ice and the surrounding sea. A bergy bit, small enough to be hidden in the swell, is invisible to radar and can strike a steel hull with a force that leaves the crew almost no warning and virtually no time to respond. The process by which icebergs acquire their shapes is a long and complex one. When a piece of ice first breaks from a glacier or ice shelf, it usually has a shape that reflects the structure of its parent. As it drifts and melts, it begins to evolve. Waves undercut its base, creating an overhang that eventually collapses. Wind and rain and sun erode the upper surface. Meltwater runs down the faces and refreezes in cracks. The ice responds to changes in temperature and pressure in ways that produce fractures and hollows and arches and caves, all of which develop and change as the berg continues its slow journey toward warmer water. The most dramatic transformation an iceberg can undergo is rolling. As it melts differentially, faster on the parts most exposed to sun and wave action, the distribution of its mass changes. Eventually, the imbalance becomes critical. The berg tips, rolls, and finds a new equilibrium position. The roll can happen with extraordinary speed, even in bergs of great size, and it releases energy that sends waves radiating outward across the surrounding sea. A berg that rolls near a ship creates a hazard that is sudden, unpredictable, and essentially unavoidable. It is one of the reasons that even experienced polar mariners maintain distances from icebergs that might seem excessive to an outside observer. Icebergs are, in the most literal sense, pieces of Antarctica traveling through the ocean. The ice they are made of fell as snow on the continent thousands of years ago. In some cases, tens of thousands of years ago. It was compressed and recrystallized as more snow accumulated above it, its air bubbles squeezed into tiny pockets of ancient atmosphere that carry the chemical signature of the world at the time they were trapped. The iceberg carries all of this with it as it drifts. It is a time capsule as well as a geological specimen, and as it melts, it releases not just cold fresh water into the ocean, but a history of the atmosphere that predates human civilization by immense margins. Currents carry these frozen giants far from where they were born. A piece of Antarctica can drift into open sea, slowly melting, rotating, and reshaping itself while still carrying the memory of the continent. Around them, wildlife may gather where ice meets water. Seals rest on floes. Birds cross the wind. Whales move through nearby feeding grounds, showing that danger and life often share the same cold edge. The beauty around these bergs is almost unreal. Blue shadows cut through white ice. Waves flash against frozen walls. Pale towers glow under grey skies, making danger look calm enough to be mistaken for stillness. But icebergs can roll, crack, and split without warning. When balance changes, the quiet sculpture becomes motion, sending waves outward and revealing how much force was hidden inside its frozen silence. The Antarctic Edge becomes cinematic through ice itself. These white fortresses are beautiful because they seem frozen, and threatening because they never truly are, always drifting, breaking, hiding, and moving through the cold sea. For humans, every iceberg demands distance and respect. Its visible face may look measurable, but its underwater body's sudden movement and drifting path keep it from ever being a simple object on the sea. Ice shelves, the continent's frozen roof over the sea. Beyond the drifting icebergs, the Antarctic Edge reveals its most consequential structures, the ice shelves. These are not sea ice, and they are not glaciers in the conventional sense. They are extensions of the continental ice sheet that have flowed out over the ocean and now float on the water, tethered at their landward edge to the grounded ice behind them, and exposed at their seaward edge to the full force of the ocean. An ice shelf seen from above looks like land. It is flat, white, and extends to the horizon without any visible feature that would suggest it is anything other than solid ground. The largest ice shelves appear in satellite imagery as continuous white surfaces of enormous extent. The Ross Ice Shelf alone covers an area comparable to France. Standing on its surface, you would see nothing but flat white in every direction. You would have no visual indication that beneath your feet, instead of bedrock, there is dark, moving ocean water. This is the fundamental character of an ice shelf. It looks like land while being something entirely different. It is an interface, a meeting place, a zone where two utterly different environments, the frozen continent and the marine world, exist in close, consequential contact. Above the shelf is the Antarctic atmosphere, cold and dry and often violent. Below the shelf is ocean water that is cold by any ordinary standard, but is warmer than the overlying ice, and is moving, carrying heat, salt, and nutrients in currents that circulate beneath the frozen roof in cavities that can extend for hundreds of kilometers inland. An ice shelf can look like solid land from above, flat and white for distances the eye cannot measure. But beneath it, black ocean moves through cavities, touching the frozen underside in silence. These shelves matter because they connect two worlds. Behind them lies grounded ice flowing from the continent. Below them lies seawater, tide, current, and warmth pressing against Antarctica's outer frame. In this way, an ice shelf works like a giant frozen buttress. It does not stop the glacier behind it completely, but it can slow the flow, adding resistance where ice tries to move toward the sea. The structural role of ice shelves in the Antarctic system was not fully appreciated until relatively recently. They hold back the glaciers and ice streams that flow toward them from the interior of the continent, and their removal can have consequences that ripple far beyond the local geography. The danger begins when that buttress weakens. Cracks lengthen, thin zones spread. Warm water can melt from below, reducing the strength of a structure that once helped hold the edge together. When a shelf fractures, the change can feel sudden, but the process often begins quietly. Hidden melt, flexing tides, surface cracks, and stress lines prepare the break long before the final split appears. A shelf collapse does not only remove floating ice, it can change the behavior of glaciers behind it, allowing grounded ice to move faster toward the ocean once the frozen break has been removed. This dynamic was observed directly after the Larsen B ice shelf on the Antarctic Peninsula collapsed in 2002, losing thousands of square kilometers of ice surface in a period of just a few weeks. The glaciers that had previously flowed into it accelerated by factors of 2 to 8 times their previous velocities. The ice that had been held back was suddenly free to move, and it moved. This is why the behavior of ice shelves matters globally, not just locally. The ice they hold back is grounded ice, ice that sits on bedrock above sea level. When grounded ice reaches the ocean and melts or calves, it adds water to the ocean that was previously stored on land. It raises sea levels. The total sea level rise potential stored in the grounded ice that Antarctic ice shelves are currently helping to restrain is measured in meters. Not all of it would be released in any realistic near-term scenario, but even a fraction of it released into the ocean over the coming century would fundamentally reshape every coastline on the planet. The processes by which ice shelves weaken are multiple and interacting. Basal melting, the erosion of the shelf's underside by ocean water circulating in the subshelf cavity, is increasingly recognized as the most important of these processes in many regions. When warmer water from the deep ocean intrudes beneath a shelf, it can melt ice from below at rates that cannot be seen from the surface, creating a shelf that looks intact and solid while becoming progressively thinner and weaker from underneath. Surface melt is another mechanism. Pools of liquid water forming on the tops of ice shelves percolate into cracks and fractures in the ice, dramatically accelerating the rate at which those fractures propagate. The mechanism is called hydrofracture. The weight of water in a crack generates stress at the crack tip that exceeds the fracture strength of the ice, causing the crack to extend further, which allows more meltwater to enter, which generates more stress. A feedback that can propagate a fracture through an entire ice shelf with startling speed. Watching an active calving front, the seaward edge of an ice shelf from which icebergs are regularly breaking, is an experience that combines the visual grandeur of Antarctica with an immediate physical reminder of the forces at work. The calving front may be a wall of ice that rises 20 or 30 meters above the waterline, its face scarred and fractured, its base periodically undercut by wave action. Cracks propagate through the ice with sounds that carry across the water, a deep, reverberant cracking that is felt as much as heard, followed sometimes by a groan or a boom as sections shift against each other before finally separating. When a large section calves, the event is sudden and dramatic in ways that the slow processes preceding it would never suggest. A section weighing millions of tons falls forward or drops down, displacing an enormous volume of water and sending waves radiating outward across the bay in every direction. The noise is extraordinary, a sound that has no direct parallel in ordinary terrestrial experience. And then the new iceberg, still rocking from the energy of its separation, begins its long drift away from the continent that created it. Under every shelf is an unseen world of dark water, pressure, current, and melt. Above every shelf is wind, snow, cold light, and cracks that can turn a quiet white plain into a warning. The ice shelf becomes the continent's giant roof over the sea, beautiful, massive, and fragile, holding Antarctica's edge together while ocean and time test its strength from below. Under the ice, the hidden ocean beneath the frozen roof. There is a world beneath the ice shelves that very few human beings have ever seen, and that science is only beginning to understand in any detail. It is a world of perpetual darkness, slow currents, cold pressure, and hidden biology. A world that exists at the intersection of the frozen continent above and the deep ocean below, in a space where the ordinary boundaries between different environments are negotiated in ways that are not visible from the surface and not accessible by ordinary means. Below the ice shelf, the geometry of the world inverts. The sky that normally defines the upper limit of experience has been replaced by a ceiling of blue-white ice that may extend for dozens or hundreds of kilometers without a break. The surface that a diver or a robot encounters beneath the shelf is not the bottom of the ocean, but the underside of the shelf itself, a complex, sculpted, constantly changing surface of ice that is simultaneously being added to from above by the compression of the glacier and eroded from below by the ocean water that circulates against it. The light in this under-ice world, where it exists at all, enters only through the thinnest parts of the shelf, or through leads and cracks near the calving front. It is a diffuse, blue-green light that filters downward through the ice in fractured rays, illuminating a few meters of water before the darkness beyond absorbs it completely. Here, the Antarctic Edge becomes vertical and hidden. The eye loses sky, horizon, and distance, meeting instead a cold chamber where ice hangs overhead and the ocean continues its quiet work underneath. In that dimness, shapes appear slowly, drifting particles, pale animals, and shadows moving through water colder than memory. Currents slide beneath the ice shelf with patient force. They carry salt, oxygen, heat, and nutrients into dark cavities, touching the frozen underside where small changes can matter to the whole edge above. The currents beneath the ice shelf are driven by a combination of tidal forcing, density differences between water masses, and large-scale circulation patterns of the Southern Ocean. They are slow by the standards of surface currents, often measured in centimeters per second rather than meters per second, but they are persistent and consequential. They carry heat into the subshelf cavity and cold water out of it. They transport oxygen from the surface ocean, where it is replenished by wave action and photosynthesis into the oxygen-depleted regions deep in the cavity where no photosynthesis occurs. Understanding the circulation patterns in these subshelf cavities is enormously difficult, partly because they are physically inaccessible by conventional means, and partly because the cavities can extend for hundreds of kilometers inland. Scientists have used hot water drilling to bore through hundreds of meters of ice and lower instruments into the cavity below, collecting temperature, salinity, and current measurements at single points. They have sent small autonomous underwater vehicles through access holes to make wider surveys of the cavity environment. Each approach reveals something. But the picture that emerges from these sparse measurements must be extrapolated across spaces that dwarf the coverage of any observational network yet deployed. This under-ice world is not empty. Fish, invertebrates, microbes, and strange cold water life survive in narrow limits, adapted to darkness, pressure, low temperature, and food that arrives unevenly from elsewhere. Some creatures cling to the underside of ice or settle on the seabed below, living in a place that seems sealed from the planet itself. Their survival proves the Antarctic Edge is layered, hidden, and not lifeless. The diversity of survival strategies represented in these communities is a testament to the extraordinary adaptability of life, and a reminder that the criteria we use to identify habitable environments must be continually revised in light of where life is actually found. For seals and penguins, openings in the ice become gateways between worlds. They dive from the bright surface into blue shadow, chasing prey through corridors that humans can only enter with machines. Under the shelf, danger feels different. There are no roaring waves, no visible cliffs, only darkness, pressure, hidden current, and a frozen ceiling that can extend for kilometers beyond ordinary sight. Scientists reach this realm with cameras, sensors, and robots, but each light reveals only a small circle. Beyond the beam, the under-ice ocean continues larger, darker, and more complex than surface images suggest. So this world reveals itself slowly, not only ice above and waves outside, but dark water beneath the frozen roof, where slow currents, hidden life, and melting contact quietly shape the continent's border from within. The Ice Edge ecosystem, where the frozen world feeds the living one. Nowhere in Antarctica is the relationship between the physical environment and the biological world more direct, more immediate, and more dramatic than at the ice edge itself. The fluctuating boundary between sea ice and open water that advances northward through the winter and retreats southward through the spring and summer. The ice edge is not a barrier, it is a generator. The processes that occur along it create conditions of extraordinary biological productivity that support one of the most important marine ecosystems on Earth. When the ice begins to retreat in spring, the changes happen quickly, and they happen in a specific spatial pattern that is critical to the productivity of the system. As the ice edge moves southward, it exposes open water to sunlight for the first time in months. The water beneath the retreating ice is cold, relatively fresh from the melt, and laden with nutrients that have accumulated during the winter. The combination of nutrients and returning sunlight creates conditions for explosive phytoplankton growth. The ice edge bloom is one of the most intense episodes of biological production in any ocean. A rapid, massive increase in phytoplankton biomass that turns the water green-gold in satellite imagery and creates a band of intense productivity that follows the retreating ice edge southward as spring advances. Light enters, nutrients mix, plankton blooms, and krill turn cold water into one of the most important meals in the Southern Ocean each season. This bloom is the foundation of everything that follows. The phytoplankton are eaten by zooplankton and, above all, by Antarctic krill, small crustaceans that have evolved to exploit exactly this kind of intense, seasonal, spatially structured food source. Krill aggregate at the ice edge in densities that are almost impossible to describe without losing intuitive meaning. Billions of individuals per square kilometer, swarms so dense they register on sonar as solid reflectors, schools that turn the water pinkish-orange at the surface. In a world of superlatives, Antarctic krill swarms are among the most extraordinary concentrations of animal life on the planet. The krill, in turn, attract everything that feeds on krill. And in the Southern Ocean, that means almost everything. Penguins make long foraging journeys from their colonies to reach the ice edge feeding grounds, some species traveling hundreds of kilometers on trips that may last days or weeks. Seals arrive and patrol. Seabirds circle and read the surface like a map of invisible food. A patch of open water, a sudden flock gathering, or a dark line beside ice can reveal where the hidden food chain has begun rising toward daylight again. Whales reveal the scale of this concentrated life. They arrive when krill swarms thicken, turning the Antarctic edge into a seasonal banquet powerful enough to draw giants from distant ocean routes. Blue whales, the largest animals that have ever lived on Earth, feed on krill with a selectivity and an efficiency that is astonishing given their size. A blue whale at full feeding pace may consume 4 tons of krill in a single day, filtering them from the water through its baleen plates in long, lunging passes through dense aggregations. Humpback whales migrate from tropical and subtropical waters, where they breed and give birth, crossing the Southern Ocean to reach these feeding grounds each summer, bulking up on the extraordinary krill concentrations in preparation for the months ahead when food will be far scarcer. Life here is not spread evenly across the frozen world. It clusters where ice loosens, water moves, and light returns, proving that abundance in Antarctica depends on brief openings and exact timing. This concentration makes the edge both beautiful and tense. Penguins, seals, whales, birds, krill, and fish crowd into a narrow zone where survival depends on staying close to a moving boundary line. The Antarctic edge is dangerous because it changes, but that same change makes it alive. Ice breaks, water opens, food gathers, and the whole system responds quickly before the short season closes again. The ecosystem here functions almost as a single organism, each component responding to and shaping all the others, the biology and the physics locked together in a relationship of mutual dependence that has been refined over millions of years. Life at the ice edge is concentrated in space and time, in ways that make the ecosystem simultaneously breathtaking in its abundance and precarious in its fragility. The abundance is a function of the concentration, the way that the physical processes of the ice edge draw organisms together from across wide areas and focus them into a relatively narrow zone. The precariousness is a function of the same thing, the dependence of the entire system on the timing, extent, and productivity of the ice edge bloom, all of which are sensitive to changes in sea ice extent, timing of the seasonal sea ice cycle, and ocean temperature. The ice edge is not a quiet border. It is a feeding line where frozen margin becomes biological frontier. At the places where the sea can breathe through ice, Antarctica reveals not emptiness, but a dense and urgent web of life. One of the richest, most productive, and most consequential marine environments anywhere on the surface of the Earth. Penguins between two worlds. Of all the animals that live and feed at the Antarctic edge, penguins make the dynamic of this environment most visible, most immediate, and most emotionally accessible to the human observer. They are, in their appearance and their behavior, creatures of apparent paradox, built for an environment that combines the most demanding features of two utterly different worlds. On land, penguins are ungainly. Their upright posture and short legs make walking across ice or rock a process that is clearly effortful, sometimes almost comical in its awkwardness. They fall over, they slip on ice. They navigate steep gradients with a shuffling, stumbling urgency that seems poorly matched to the demands of the terrain. Watching a column of Adelie penguins waddling across an ice field toward the water, pausing occasionally to look around, resuming their march, stopping again, moving in the irregular start-stop rhythm of animals that are slightly uncertain about their next step. You might wonder how creatures that seem so poorly designed for their environment could possibly be as successful as they are. And then one of them enters the water, and everything changes. The transformation is immediate and absolute. The awkward, waddling creature on the ice becomes something sleek, fast, and utterly precise in the water. A penguin swimming is not struggling against its environment, it is expressing its deepest adaptation to it. The wings that are useless for flight in air become powerful, efficient hydrofoils in water. The body that looks bulky and unstreamlined on land presents the minimal drag profile of an animal whose evolutionary history has optimized it for aquatic locomotion over millions of years. A penguin underwater moves with a speed and a grace that are genuinely astonishing, capable of sustained swimming speeds that would challenge a human sprinter and burst speeds that exceed most fish. This dual nature, the awkwardness on land and the mastery in water, is not a design flaw. It is the expression of an evolutionary solution to a problem that no other group of birds has solved in quite the same way. Penguins have committed so completely to aquatic life that they have sacrificed their capacity for aerial flight entirely, accepting the vulnerability that this creates on land in exchange for the extraordinary effectiveness it gives them in the water. From the colony, their movement looks almost fragile. small bodies crossing white space in lines, pausing against wind, then continuing toward the edge where solid worlds suddenly give way to water below. At the shoreline, the decision becomes physical. One penguin enters, then another follows, and the quiet march turns into a plunge from air and ice into a blue-black hunting world below. Underwater, the same bird becomes completely different. Awkward steps vanish, wings become blades, and penguins fly through cold water after krill and fish with a speed the surface never suggested. But the sea that feeds them is also the sea that hunts them. Leopard seals wait near entry points, using patience, shadow, and timing to turn the penguin's return route into a narrow zone of risk. A leopard seal will patrol near a penguin entry point for hours, exploiting the concealment offered by the underwater environment to wait for an opportunity. The penguin that hesitates at the ice edge, waiting for another penguin to enter first, is not being timid. It is being intelligent, reducing its individual probability of being the first, most vulnerable animal in the water when a predator may be waiting below. The social behavior of penguins at the ice edge reflects this tension between the need to enter the water to feed and the risk that the entry involves. Colonies approaching the water will often mass at the edge, individuals jostling and crowding without any of them willing to be first. The dynamics of this behavior are recognizable to any human observer. The reluctance to lead, the waiting for someone else to demonstrate that it is safe, the sudden surge of movement once the first animal has gone and the others conclude that the risk must be acceptable. Each journey begins with a difficult exchange. Leaving the ice means reaching food, but it also means entering cold sea, hidden current, leopard seals, and distances that can punish hesitation fast. Every successful dive is tied to the colony behind it. Food caught in dark water becomes energy for chicks on the ice, linking the hidden ocean to voices, hunger, and survival above the frozen surface. Distance makes the struggle heavier. A feeding ground may shift with ice, wind, or krill, forcing penguins to travel farther while still returning before cold, exhaustion, or weather changes the path. For some penguin species and in some regions, shifts in sea ice extent and timing are requiring penguins to travel greater distances to reach their food, burning more energy in transit and returning with less surplus to feed their chicks. The consequences for breeding success can be significant. This is why penguins are more than symbols of Antarctica. They are commuters between worlds, carrying the tension of the edge in their bodies. Land for breeding, sea for food, and danger between both. In each trip, Antarctica becomes alive, not as a silent white continent, but as a moving border where survival must cross itself again and again, day after day, season after season, generation after generation. Watching a penguin complete a foraging journey, entering the water at the colony's edge, disappearing into the blue-black depths, returning hours or days later with a belly full of food, scrambling back onto the ice with the urgency of an animal that knows chicks are waiting, is to observe one of the most fundamental rhythms of the Antarctic system. It is the daily, seasonal, generational pulse of an ecosystem that has been operating in broadly its current form for millions of years, and that is now changing in response to a world that human activity is reshaping. Humans at the edge, witnesses in a system too large to command. Human beings have been coming to the Antarctic edge for roughly 2 centuries. First in the wooden ships of the sealers and whalers who harvested the wildlife of the Southern Ocean, with a thoroughness that brought multiple species to the brink of extinction. Then in the vessels of the explorers who mapped the coastline and made the first landings. And now in the research icebreakers, supply vessels, and expedition ships of the modern era. In all of this time, the relationship between humans and the Antarctic edge has been defined by a single fundamental asymmetry. The environment is the master, and the human visitor is the guest. This is not a metaphor. It is a physical reality that every person who has spent time at the Antarctic edge will confirm from experience. The Southern Ocean does not adjust its weather for the convenience of research schedules. The sea ice does not open a lead simply because a ship needs to reach a particular destination by a particular date. The calving ice shelf does not warn nearby vessels before it releases a section of its face. The leopard seal does not pause its hunt to accommodate the photographer attempting to capture the moment. Research ships move through cold bays like small instruments inside a planetary laboratory. Around them, ice shelves, bergs, wind, and dark water remind every crew that observation here always depends on permission from weather. Icebreakers can open a route for a while, but they never truly own it. Behind the hull, ice can close again. Flows can shift. The ocean can rebuild the barrier as if human passage were only a brief interruption. The human presence at the Antarctic edge is characterized by a kind of persistent negotiation between intention and reality, in which reality wins most of the rounds. A field season planned months in advance may be entirely reorganized by ice conditions that prevent access to the intended research site. A sampling program designed to collect measurements from a specific location may be abandoned when the ice closes in before the work is complete. Survey aircraft cross the white edge from above, mapping cracks, heat, ice flow, and hidden change. From the sky, Antarctica becomes readable in patterns, yet still too vast for any single flight to fully explain. Flying over the continent and its margins, aircraft equipped with radar altimeters and ice-penetrating radar can map the surface of the ice sheet, the topography of the bedrock beneath it, the thickness of the ice in ways that would require centuries of surface surveying to accomplish. The results of these airborne surveys have revealed features of the Antarctic ice sheet that nobody suspected before the technology existed to see them. Vast subglacial lakes, buried beneath kilometers of ice, where liquid water persists at temperatures well below the freezing point of fresh water because of the pressure above and the geothermal heat from the rock below. Beneath the ice, robots enter the unseen frontier. Their lights move through black water under frozen roofs, recording melt, current, and strange life in places human bodies could never survive directly. These autonomous underwater vehicles can navigate beneath ice shelves for hours or days at a time, collecting data from environments that would be inaccessible to human divers. They map the underside of ice shelves in 3 dimensions, revealing the sculpted topography of basal melt channels and the locations of regions where warm ocean water is in most active contact with the overlying ice. Coastal research stations feel like fragile outposts at the edge of a moving continent. Heat, fuel, communication, and timing keep them alive, while the surrounding ice proves that comfort here is never natural. Every measurement carries difficulty. A sensor must survive cold, a drill must reach water, a ship must wait for sea ice, and a team must accept that the Antarctic Edge rarely reveals anything on human schedule. Satellites have transformed the study of Antarctic change more than any other single technological development of the past half-century. From orbit, satellites can monitor the entire continent continuously, measuring changes in ice sheet elevation, sea ice extent, ice flow velocity, and ice shelf temperature. The satellite record of Antarctic sea ice extent now extends for more than 40 years, long enough to reveal trends that are statistically robust and that tell a story of change that is real, significant, and in some regions rapid. The goal of all of this effort is not conquest, but understanding. Scientists listen to ice through radar, to water through sensors, to wildlife through movement, and to weather through every change in wind, cloud, and sea state. This human presence makes the edge feel even larger. The more machines measure, the more complex the system becomes: ice above, ocean below, life between them, and change moving through all layers at once. So, humans at the Antarctic Edge become witnesses, not masters. They arrive with ships, aircraft, robots, and stations, but the real lesson is humility. To understand this frontier, we must first learn how to listen to the ice, to the ocean, to the animals, and to the slow, patient voice of a continent that has been speaking in the language of change for longer than our species has existed to hear it. The edge in a changing world. Antarctica has always been a place of change on geological timescales. The ice sheet has grown and contracted through multiple glacial cycles. Ice shelves have formed and collapsed and reformed over periods of thousands of years. The coastline has been shaped and reshaped by forces that operated over epochs that dwarf any human timescale. Change is not new to Antarctica. What is new is the pace of change and the driver of it. The evidence that the Antarctic system is changing in ways at least partly attributable to human influence on the global climate is now substantial and growing. The Antarctic Peninsula has experienced some of the most rapid atmospheric warming recorded anywhere on Earth over recent decades. The sea ice around the peninsula has changed in extent and timing. Ice shelves that had been stable for thousands of years have collapsed. Penguin populations have shifted in distribution and changed in abundance. Glacier flow rates have accelerated. The changes are real, they are measured, and they are ongoing. In West Antarctica, the situation is particularly closely watched because of the geometry of the ice sheet in that region. Much of the West Antarctic ice sheet sits on bedrock that lies below sea level. In some places, hundreds of meters below sea level, and the ice sheet bed slopes downward away from the coast toward the interior. This geometry creates the potential for what glaciologists call marine ice sheet instability, a feedback process in which the retreat of the grounding line allows warmer ocean water to access the ice sheet's base at progressively greater depths, potentially driving further retreat in a self-reinforcing cycle. Whether this instability is currently active in parts of West Antarctica is one of the most consequential questions in climate science, and the answer is not yet fully known. The data suggest that some glaciers in the Amundsen Sea sector are losing ice at rates that have accelerated significantly in recent decades, and that may already have passed a threshold from which recovery is not possible on any human-relevant timescale. If this is the case, the sea level rise contribution from West Antarctica over the coming centuries may not be a matter of human choice. It may already have been set in motion by the changes that have already occurred. The sea ice changes around Antarctica are more complex in their pattern. For most of the period of satellite observation, total Antarctic sea ice extent was increasing slightly, a trend that puzzled scientists, since a warming world was expected to reduce sea ice. The explanation involves complex regional patterns of change, the role of ozone depletion in altering atmospheric circulation, and the influence of freshwater from melting glaciers and ice shelves on ocean structure. More recently, the trend has reversed dramatically, with Antarctic sea ice reaching its lowest extents on record and raising questions about whether a new regime of reduced sea ice is establishing itself. The implications of reduced sea ice for the Antarctic ecosystem are significant. The ice edge ecosystem that has been described here, the ice edge bloom, the krill aggregations, the penguin and seal and whale feeding, depends on the existence of a sea ice boundary to organize it. If the sea ice retreats earlier and returns later, the seasonal window of high productivity may shift in ways that are not easily accommodated by animals whose breeding cycles have been entrained to the historical pattern of sea ice advance and retreat over evolutionary timescales. The Southern Ocean's role in the global climate system extends beyond its relationship with Antarctic sea ice and glaciers. It is one of the most important regions for the uptake of atmospheric carbon dioxide, absorbing a disproportionately large fraction of the excess carbon dioxide that human activity has added to the atmosphere. As the Southern Ocean warms, its capacity to absorb carbon dioxide may change. As the circulation patterns shift, the pathways by which surface water carrying dissolved carbon reaches the deep ocean may be altered. As the biology of the system responds to changing conditions, the efficiency of the processes that export carbon to depth may increase or decrease in ways that feed back to atmospheric concentrations and, through them, to the rate of global warming. The Southern Ocean is not a passive recipient of climate change. It is an active participant in the system that drives it, and its future behavior will shape the trajectory of the global climate in ways that are still being worked out by the science. The storms of the future may be more intense. The ice may retreat faster than the models have projected. The species that have evolved to live in a world organized around a particular pattern of sea ice may find themselves in a world that no longer matches what their biology was built for. The warming that is happening now will still be shaping the Antarctic system centuries from now, because the ocean warms slowly and the ice sheet responds on timescales that dwarf any human political or economic planning horizon. Choices made today about emissions, about energy systems, about land use and consumption will determine how much additional warming the Antarctic system must absorb in the coming centuries, and how much additional ice will flow into the sea as a result. The connection between the decisions made in cities thousands of kilometers from the nearest iceberg and the future of the Antarctic Edge is real, measurable, and consequential in ways that no amount of geographic distance can diminish. The edge as mirror and measure. There is a dimension of the Antarctic edge that is not captured by any measurement or model, a dimension that can only be accessed through direct experience, and that has been described imperfectly by everyone who has spent time there. It is the quality of the place as a mirror, a surface against which human beings see themselves and their civilization reflected with unusual clarity. To be at the Antarctic edge is to be at the edge of the human world. It is to be beyond the reach of the infrastructure, the supply chains, the communication networks, the social structures that normally constitute the context of human life. The nearest city is thousands of kilometers away. The nearest emergency services are measured in days of travel time. The world contracted to the vessel, the camp, the ice, and the people immediately around you is not a metaphor. It is the literal reality. In this contracted world, the Antarctic environment is not a backdrop. It is the entire context. The weather is not an inconvenience. It is the determining factor in every decision. The ice is not scenery. It is the medium in which everything takes place. The ocean is not an abstraction. It is the source of all risk and all wonder simultaneously. People who spend extended time at the Antarctic edge almost universally describe a shift in their sense of proportion, a recalibration of what matters and what does not that persists long after they have returned to their ordinary lives. Antarctica also teaches, through its biological richness, what it looks like when an ecosystem is functioning at something closer to its natural capacity. The concentrations of wildlife at the ice edge, the penguin colonies of hundreds of thousands of individuals, the krill swarms that extend for kilometers, the whale densities that remind the observer of historical accounts of the pre-exploitation Southern Ocean, are a window onto a world that functions differently from the depleted ecosystems that most of humanity's experience is shaped by, not pristine, not unchanged by human influence, but significantly more abundant, significantly more complex, and significantly more capable of the kind of ecological spectacle that was once common across the world's oceans. The Antarctic Treaty of 1959 and the subsequent agreements that have added to it represent one of the more successful examples of international environmental governance in the history of the modern world. By setting aside Antarctica for peaceful, scientific purposes, by prohibiting national territorial claims and military activities, and by establishing frameworks for environmental protection that have become increasingly comprehensive over the decades. The treaty has kept Antarctica from the extractive exploitation that would otherwise have been its fate. These are imperfect achievements, contested and incomplete. But they are real achievements. Antarctica has been, for the duration of the treaty era, a place where the international community has chosen, deliberately, to subordinate extractive economic interests to the goal of scientific understanding and environmental preservation. That choice reflects something about what humanity, at its best, is capable of deciding about its relationship to the natural world. The question of whether that choice can be sustained in the face of increasing economic pressure is one of the most consequential international environmental questions of the coming decades. As climate change makes resources that were previously locked beneath ice more accessible, as national interests in Antarctic territory resurface in the political landscape of the mid-21st century, the Antarctic Treaty will face challenges that its architects did not fully anticipate, and that the current generation of treaty parties must navigate with the same humility that the physical environment demands. The Edge enduring. In the end, after all of the science and the policy and the history and the biology has been accounted for, the Antarctic Edge remains something that exceeds the capacity of any of these frameworks to fully contain or explain. It is a place of such physical extremity, such biological abundance, such geological grandeur, and such climate significance that no single discipline of human understanding is adequate to it. The ice that breaks from the calving front and begins its drift northward carries within it the physical record of the world's past. The krill that filter through the waters of the ice edge carries within it the biological energy that sustains some of the largest animals on Earth. The wind that races across the Southern Ocean carries within it the atmospheric energy that is redistributed around the planet, influencing weather patterns in places thousands of kilometers away. The change that is occurring at the Antarctic Edge carries within it the consequences of choices made by billions of people who have never seen an iceberg, who have never felt the wind off the polar front, who have never watched a penguin enter the ocean at the edge of the frozen continent. All of these things are connected. The Antarctic Edge is not remote from the human world. It is connected to it by physics, by biology, by ocean currents, by atmospheric circulation, by the global carbon cycle, by the sea level rise that is already reshaping coastlines on every inhabited continent. What happens at the edge of Antarctica matters to everyone, everywhere, whether they know it or not. The ice continues to move. The ocean continues to warm. The shelves that have held the glaciers in place for thousands of years are thinning and fracturing and, in some cases, collapsing. The sea ice that has organized the ecosystem and protected the ocean surface for millennia is changing in ways that are disrupting the biological rhythms that species have evolved over evolutionary timescales to match. And yet the penguins continue their daily crossings. The seals continue their hunts. The whales continue their migrations from tropical breeding grounds to polar feeding grounds, and back again, following the energy gradient of the ocean as they have always done. The albatrosses continue their vast, windswept circuits of the Southern Ocean, using the gradient between wind near the water surface and wind aloft to soar for hours without a wing beat, covering distances that no other bird approaches. The edge of Antarctica is a place where the natural world continues to operate at something close to its full capacity, where the scale of ecological process and geological change dwarfs the scale of human presence, where the forces that have shaped the planet over billions of years are still visibly, dramatically, actively at work. It is a reminder, perhaps the most vivid and undeniable reminder available to human experience, that the Earth is not a stage set designed for human drama. It is a living, dynamic, ancient system of extraordinary complexity and extraordinary fragility, and the choices that the human species makes in the coming decades will determine how much of it remains intact for the generations that come after us. The continent moves. The ice speaks in the language of fracture and flow. The ocean answers with warmth and current and the slow, inexorable rising of the sea. And at the edge, where all of these processes converge, the planet reveals itself as what it has always been. Something vast, alive, indifferent to our presence, and more necessary to our survival than we have ever fully acknowledged. When calving begins, silence turns into impact. A wall of blue ice falls, the bay erupts, waves spread outward, and the continent shows that even frozen landscapes can move with sudden violence. Beneath the ice, the unseen world keeps breathing. Dark currents touch the shelf from below, particles drift through cold water, and strange life survives where no surface image can explain the whole story. At the ice edge, life concentrates with urgency. Krill gather, penguins dive, seals patrol, seabirds circle, and whales rise through cold water, turning a harsh boundary into one of Earth's richest feeding lines. Their small bodies cross ice, vanish into black water, return with food, and repeat the journey between colony and sea, as if survival itself were a daily crossing. Human ships and stations remain tiny against this scale. Icebreakers, robots, aircraft, and sensors can measure pieces of the system. But every answer reveals a border too vast and changeable to control. The more we measure, the more we understand how much remains beyond our measure. The Antarctic Edge closes as the place where Antarctica is no longer silent. At its rim, ice cracks, bergs drift, water moves, wildlife gathers, and the planet keeps breathing through a white-gray frontier that has been here since long before any human eye first saw it, and that will continue long after the last research vessel has turned and sailed away. This is the Antarctic Edge. Unforgiving, irreplaceable, and unlike anywhere else on Earth. The border where icebergs and wind shape the land, and where the land, in return, shapes the future of the world.